Hello all. So in this session we will be discussing the next topic, region-based convolutional neural networks and fast region-based convolutional neural networks. So far in the previous two sessions we have talked about what object detection is and the general framework which is required for object detection, where we have discussed the first component for object detection required is region proposals, that is nothing but region of interest, which shows the probability of target contained within that boundary box, and each boundary box is represented by the coordinates x, y, w, h. The second component which is related to object detection is feature extraction, and the third component involved is non-maximum suppression, where the boundary box overlap with the ground truth boundary box will be calculated, and if it is beyond the threshold value, then that boundary box will be used for further processing, or else that boundary box will be suppressed. And also we have discussed evaluation metrics used in object detection. Now in this session we will talk about taking these framework into consideration. We will talk about region-based convolutional neural networks. Now why do we call it as region-based convolutional neural network? Because the detection of the objects in RCNN will be revolving around the region of interest only. Hence you call it as region-based convolutional neural network. And the main difference between CNN and RCNN is CNN will process the entire image given, whereas RCNN, instead of processing the entire image, it will focus only on the subsets of the regions likely to contain the object that are nothing but the region of interest. So it concentrates only on the subsets, also called as region of interest, instead of processing the entire image. So let us start with RCNN. It is short of region-based convolutional neural networks, which was developed by Ross-Girshik in 2014. RCNN divides an input image into regions called as region proposals and then pass each proposal through a convolutional neural network to extract the features. So this is my image. RCNN will extract the region proposals from the given image, and each region proposal or region of interest will be given as input to CNN for extracting the features. So as I have 4 region proposals, I will be using 4 convolutional neural networks to extract the features. And once the features are extracted, the CNN features are used to classify the objects present and class using support vector machine. So the features which are extracted will be given as input to SVM, which is a supervised machine learning algorithm used for classification, and it will classify based on the class labels. As well as at the output, you will also have a bounding box regressor which will fine tune the object's location. Along with SVM, at the output you will have a bounding box regressor also. The main idea behind this using of this bounding box regressor is it will predict the object class and define the position of the bounding box also. So this bounding box regression adjusts the coordinates for more accurate localization. What coordinates we are talking about? Coordinates of the bounding box represented as x, y, w and h. The ground truth bounding box we have discussed in the previous session. This is the bounding box which is given by the dataset. And for example, this is the bounding box what you have predicted using selective search algorithm. So you need to find the overlap between the predicted bounding box and the ground truth bounding box. If the overlap is maximum, then this bounding box can be used for further processing. So what this bounding box regressor will do is it will fine tune the coordinates of this predicted box so that it will overlap with the ground truth bounding box. This is the main idea behind using this BBR at the output. So these are the steps involved in region-based convolutional neural networks. Looking into the architecture, you can see here you have an input image, extracting the regions called as region proposals, and the algorithm what used here for extracting the region proposals is selective search algorithm. and it is said that around 2000 region proposals will be extracted when we use this proposed method for extracting the region of interest. So these 2000 region of proposals will be wrapped together. Why do we wrap here is, one of the restriction of CNN is it will accept images with constant dimension. That is, if one image is of 224 by 224, the second image also should be of the same dimension. This is one of the restriction. So as you can see in the image, the dimensions of the boundary boxes are different. So we will convert these different dimensions into a constant dimension. For example, it can be 224 by 224, or in most of the cases it can be 227 by 227 as well. So all these region proposals will be wrapped so that all 2000 region proposals are of same dimension. These region proposals are given as input to CNN to extract the features. The extracted features are given as input to SVM for classification. These are the steps which are involved in region-based convolutional neural networks. These are the 4 component: extract region of interest, feature extraction, classification module, and localization module, which is done by a regressor here, a bounding box regressor. Looking at step-by-step process, this is the input image. Next, what do? Is we will extract the region of interest, and the method which is used to extract region of interest is selective search algorithm. For an example, only 3 proposals are given here, but around 2000 region proposals will be extracted from the given image using the algorithm. So let us discuss the selective search algorithm. It is a greedy search algorithm that is used to provide region proposals that potentially contain objects. It tries to find areas that might contain an object by combining similar pixels and textures into rectangular boxes. That is, it will combine within the given image, it will either take pixels into consideration and combine. For example, in the image, it will combine all the pixel values into rectangular boxes, or it may combine all the textures into one box, or it may combine all same colors into one single box. In such a way, this selective search algorithm will be used to generate region proposals. Here is an example. You have an image with the different objects here. Segmentation is done where you can see here that it is combining the images, or the combining the objects within the image belonging to same color, same texture, or even same pixel value. So you can see here the similarities between all the neighboring regions are calculated, and the 2 most similar regions are grouped together, and it will search for the new similarities in the neighborhood. This process is repeated until the entire object is covered into a single region. You can see here, this is the input image. These are the proposed region of proposals. Then among all these, it will combine region of proposals containing same pixels, same texture, and even same color. So after first iteration, you can see reduced region of proposals, and finally after few iterations, you will be left out with these many boundary boxes, also called as region proposals, in the input image. This is what selective search algorithm is used to generate region proposals from the given image. One more example. Consider this image. These are the 3 region proposals: green, red, and yellow. So the probability of finding object in green and red is more compared to that of yellow. Hence, green and red boxes are called as region proposals. And this is my segmented image, which has many regions. After few iterations, it will combine the areas with the same texture or same pixel values and come up with few regions. And in the next level, you can see it is left out with only 2 regions, dark green and light green region. That means as we are moving from one level to other level, the number of regions get reduced. This is what happens in selective search algorithm. Now once the features are extracted, we will go for wrapping. Now what wrapping will do is, it will convert the uneven boxes, that is rectangular square boxes, those are region proposals extracted from selective search algorithm, that will be converted into constant dimensions. So these are region proposals which are generated using a selective search algorithm. And after wrapping, you can see you have constant dimensionality, and the dimensionality what required here will be either 224 by 224 or 227 by 227. Next, once the features are extracted and wrapped into a constant dimension, each region will be passed to convolutional neural network for extracting the features. Now, how are these features extracted? To extract the features, we make use of predefined models. So, in this example, I'll explain the example using an AlexNet model which has 8 layers. You can use VGGNet, you can use ResNet also. Here I am extracting features using AlexNet which have 5 convolutional layers and 3 fully connected layers. But one thing what you need to remember this AlexNet model what we are using for extracting the features of region proposals, it is pre-trained model because it got trained very well for image classification but not object detection, and it got trained on ImageNet dataset. So for that we need to fine tune this AlexNet model so that you can use this predefined model for object detection. In fine tuning we have 2 steps: remove the last layer, and the second step is redefine the dataset. So this is my actual AlexNet model with 1000 classes used in ImageNet. So I will replace it with n+1 4096, n plus 1. Now why is this plus 1 used is, for example, you are having 2 class labels dogs and cats. So n will be equal to 2, but I will be adding plus 1 here. That 1 represents background. That plus 1 is added to classify if that region proposed is a background, as can be seen in this image. So hence n plus 1 will be equal to 3 when I am talking about classifying images as dog or cat. Coming to the second method involved, or second step involved in tuning, you need to redefine the dataset. This is my dataset with the different images of cats and dogs. Now we will be extracting features taking 4096,3, which is my output layer which got replaced with the original AlexNet output layer. And the first neuron will be fired when dog is given in the image. Second neuron will be fired when cat, and third neuron will be fired when it is background. This is the reason why we will be using n plus 1. So the probability of, in this bounding box, the probability of generating dog is in the first neuron, here cat for the second neuron, and background for the third neuron. So in this bounding box, as no object is present, this third neuron will be fired, indicating that it is background. Coming to the next term associated with this ground truth bounding boxes, these are the bounding boxes which the data self itself gives, and the bounding boxes what we are generating are called as predicted bounding boxes. So we will be comparing this predicted bounding box alignment with the ground truth. For example, this is the bounding box which is predicted after selective search algorithm. We need to find out the alignment of these two, that is overlap between these two bounding boxes. If it is greater than the threshold value, for example 0.5, then that will be positive, else it will be negative. That means this bounding box will be used further for processing, or else that bounding box will be suppressed. And these x1, y1 and x2, y2 for this yellow bounding box are called as top left values, and this is called as bottom right values, as we have discussed in the previous session. But last session I have told that in boundary boxes it is represented by the midpoint as x, y, and width and height as w, h. These are the coordinates which are used to represent a bounding box. Or else you can use x1, y1, x2, y2 also as indicated here. Those are interchangeable. X and y called as the midpoints, w and h are called as the width and height. If you use this, if you represent it as x1, y1 top left values and x2, y2 as the bottom right values. Anyways, it is right to represent a bounding box with either these Cartesian values or using x1, y1 and x2, y2 as the coordinates of the bounding boxes. The next step what is involved is features are being extracted by using AlexNet. Once the features are extracted, these features will be given as input to the SVM models, which are used to divide these regions into different classes. Along with, now talking about SVM, now how is SVM used? Just I'll give you a recap. We have two types of support vector machines, linear and non-linear. linear support vector machine where a straight line can be used to divide the classes. For example, this is class 1 and this is class 2. Among these two lines, which line will be considered as the best hyperplane using support vectors? The points, for example, consider B hyperplane. The point which is very close to B is this star. So let us draw a parallel line, and this point which is support vector close to B hyperplane, I will find out the distance here. Now taking D hyperplane, this point is very close to my hyperplane called as support vector, and this point is very close called as support vector. I will draw a line parallel, calculate the distance. Whichever hyperplane is having maximum distance, that hyperplane will be finalized as your best hyperplane or the best fit line which is used for classification. And the condition what you look here is max of 2 by cardinality of W. If Wx plus B is greater than or equal to 1, it belongs to class 1, and if it is less than -1, it belongs to class 2. So to the left of this hyperplane you have Wx plus B minus 1, and here you have Wx plus B is equal to plus 1. These are the different parameters. These are called as support vectors, the data points which are very close to the hyperplane, which is called as the maximum margin hyperplane, because the distance what you have calculated in this hyperplane is maximum. Coming to nonlinear SVM, this is nonlinear model where a straight line cannot be used. So we will map it using this equation so that you will get a linear model, and you can draw an hyperplane here which is dividing into both classes, and these will be the support vectors. So in such a way, support vector machines can be used to classify the given image. And the last step involved is finding the bounding box regression at the output. So you have support vector machines as well as bounding box regression which are used to adjust the coordinates so that you get accurate localization. So this is the final architecture of RCNN, which I have already told in the previous slides. Coming to the training, so far we have discussed that we have selective search algorithm, and we have feature extraction, we have SVM classifier and bounding box regression in an RCNN model. Except selective search algorithm, all these models should be trained by RCNN. Coming to the disadvantages, as I told you, 2000 region proposals will be generated. You need 2000 convolutional neural networks for feature extraction, because each ROI will be given as input to each CNN. Hence, object detection is very low and it is a multi-stage pipeline process, as well as training is very expensive in terms of space and time. To avoid these disadvantages, we will go with the second kind of RCNN called as fast region-based convolutional neural networks, which came into existence in 2014 by Ross Girschik. In the next session, we will discuss fast RCNN. Thank you all.